One of our industry's best phrases, a phrase that's launched a million projects, is how hard can it be? I'll write my own framework. How hard can it be? I'll write my own web server. That's just a network socket and a bunch of headers, right? How hard can it be? So many ambitious projects have started from a point of benevolent ignorance. And a fair few have actually finished because by the time you've gone down the rabbit hole and learnt exactly how hard it can be, you've kind of gone too far to turn back. There's one kind of project that might just be traveling in the opposite direction, that might be getting easier to build despite being obviously very hard. Databases. Databases are a huge, very difficult project with a lot of engineering and a huge footprint. At the least, for any database, you're going to need an SQL parser, an expression evaluator that borders on being a full programming language, a query planner, query optimizer, query executor, persistence, durable, optimized, fault-tolerant persistence. That's just for starters. It's big. But the very fact that I can list out a whole bunch of things that every database project needs suggests an opportunity. And in that opportunity, we find this week's topic, Apache DataFusion. It's a project that says, look, every database is going to need this bunch of default pieces. So let's build them once and for all in an extendable way so that when someone wants to write a new database, they can reuse all the standard stuff and just focus on the pieces that make their particular database special. It's a very good idea if someone is prepared to take on all that work to do it. And joining me this week is one of the people that is. My guest is Andrew Lamb. He is a very happy Rust programmer, very knowledgeable database guy, and a core DataFusion contributor. And he's going to unpack the whole project for us. And in doing so, he takes in just about everything that's interesting in the database world right now, from Arrow and Parquet and Iceberg, to DuckDB and DBT, to time series databases, streaming databases. Fascinating guy. And by the end of this conversation, I was actually thinking, building a database. How hard can it be? I'm your host, Chris Jenkins. This is Developer Voices, and today's voice is Andrew Lamb. Joining me today is Andrew Lamb. Andrew, how are you?
Very well, thank you. I'm very excited to be here.
I'm glad you could make it up from the database mines.
Oh, yes.
Crawling out armfuls of Rust code in your fingers.
But there's so much good stuff down there. There's so much more to mine. It's going to be great.
Okay, I'll keep you out of the mine for about an hour and then you can dive back down.
All right.
So you've been working on, among other things, the project you're going to talk to me about right now, you've been working on Apache DataFusion. And I think we need to start with understanding what it is and what it isn't, because sometimes I feel a bit lost in all the different databasey pieces we've got, right? Like Arrow, there's also Iceberg, there are loads of different things. What's DataFusion?
Yeah, well, to be able to start with DataFusion, I think I need to start at the really high level of what's been happening in the database landscape the last, 10, 15, 20 years. Yeah. And I think without going too much into depth, what we've seen is you saw the focus of on-prem databases, right? 10 years ago, that was basically self-managed. They were what you would call shared nothing architectures, which was a fancy way of saying you ran them on nodes that had CPU, memory, and disk, right? Like if you ever run anything in production the last 15 years, that's probably what your database looked like. Then there was a rise of distributed databases where they had a bunch of nodes that but that work together. And I think what we've actually seen now over the last 5 to 10 years is the rise of so-called disaggregated databases, which is basically driven by the rise of cheap object storage and cloud providers. So instead of tightly coupling the storage system to the compute and memory, what they've done is they disaggregated the storage. So those are fancy terms for basically saying now you put all your data on S3 or other object stores because it's so much cheaper and that handles the durability for you. And then you are able to scale up and scale down the compute resources. So Snowflake is the classic example of the first major vendor that did that, but there's a bunch of other services that you like. BigQuery has that architecture. Like I said, Snowflake is another canonical example, Databricks. So they're all basically moving largely because of the economics of how storage works on the cloud to these disaggregated architectures, right? So that's what's been happening. I'm getting to DataFusion, but I swear. So
no, I like context. It'll help me understand.
So that's sort of what's been happening in databases, and it's not dissimilar to what happened, when the transition from mainframes to mini computers to servers, is that the underlying hardware changes, and then you have to change your database architecture along the way. So, however, if you've ever implemented a database, and I have in fact done that at least once before at a company called Vertica, which was one of these distributed shared nothing databases, they're just expensive pieces of software to build. They take a lot of effort, and I think as the industry shifts again, right, towards as the underlying hardware infrastructure shifts, right, you got to re-architect your databases a little bit. There's a lot of those pieces of those databases that are still very similar. Specifically, like how you represent data on disk is fairly, whether or not it's on object store or on local disk for doing analytic workloads like crunching large amounts of the data, the organization is pretty similar. Likewise, when you bring it into memory to process it, best practice these days to take best advantage of SIMD and modern architectures is you put them in columns, right? A lot of this stuff is like columns versus rows, which we can talk about it much more. But I'm trying to make a higher level point before we go into the lower level details. Yeah. And the higher level point is like the basic patterns to build one of these high performance analytic systems is basically well understood now. And it's well understood because we've done it for at least 3 successive generations of products, right? Like you had basically the shared nothing databases like what Vertica was maybe 12, 15 years ago. ParExcel, which became Redshift, is an example of that. Greenplum was another one. And then there was a whole set of technologies in Hadoop, right, that are very similar in theory, like Impala and Pig and those systems. And then we've basically been doing it again. Now you see the same basic architectural patterns in systems like DuckDB and Snowflake and Spark, Databricks, Photon, that kind of stuff. So in my opinion, right, and I sort of have an angle here, that the engines, the fundamental techniques to build those engines are approximately the same. Obviously, the details are all different, but they're basically all columnar execution engines that have what's called vectorized processing. And so the amount of money it takes to build one, so it's well understood, but that doesn't mean it's easy, right? It still takes a lot of time and effort. It translates to money, right? And so that observation currently keeps that type of technology, like the high performance analytic engines, locked up in people who can afford it, right? So that's people who raise a lot of VC money, like tens, hundreds of millions of dollars, or it's people who, DuckDB in particular is phenomenal. But like, if you imagine, if you wanted to build another DuckDB, what would you need? What you need access to basically one of the world's premier research institutions at CWI and their grad students, right? Which is, I'm not saying that's the only thing you'd need for DuckDB, but like that certainly helps.
You certainly want to start with a team full of researchers that really know everything inside out. Right?
Yeah, and basically, like from the lab that basically invented a bunch of the underlying technology, from Peter Bonson's lab. So, however, that doesn't mean other people don't want or need that type of technology. So finally, we get into like these pieces of Apache Arrow, and Apache DataFusion, Apache Parquet. So I would say those are pieces of technology that are part of a longer term, like I think the higher level description was called composable databases or deconstructed databases. And the idea is, rather than re-implementing all basically the same techniques in a tightly integrated engine, you can reuse these components that basically follow best practice that we now understand what that is because we've done it like 3-4 times, we being the collective industry and academia. And you can then assemble systems much more quickly, but not really sacrifice performance. So does this make sense so far?
Yeah.
All right.
It seems like you're about to tell me that, no one needs to write another SQL parser. No one needs to write another how do we store columns on disk.
Rather than no one ever needs to write a new one, I think the better way I would say it is, unless that's really key to whatever product you're building, right, that's really going to be a competitive advantage, that you can take it, like you can use the existing really good open source implementations of Parquet, Arrow, DataFusion, iceberg. I'll talk about that. And then focus your innovation dollar on the things that actually really matter, right? Like for certain people in certain applications, it really is important however they've laid the data out on disk. However, for a lot of applications, like you're going to basically reinvent Parquet slowly over time. And which again might be fine, but like you should at least understand that that's what you're doing. So that's my real pitch. It's not that any particular technology of the stack, like you couldn't do better in isolation, and if you had infinite resources. However, practically speaking, you don't, and it's very, very hard to do better than what we've been able to put together in the open source world. Like there's been a lot of obsession about performance, which maybe I can talk about.
Okay. So give me a list of the features you get off DataFusion.
Yes.
So that will give me a sense of quite how much money I'd have to spend to do it myself.
Absolutely. So let me start with, instead of just DataFusion, I want to start with what we call the FDAP stack, right? This is something that we made up, but it stands for Flight, Arrow, DataFusion, and Parquet, right? So those are like the high level technologies. And if you're going to build a database system, they're the kinds of technologies you would need to find somewhere. You either build them yourself or you have to write them. So simplest thing is you got to store the data in some persistent format on disk that's fast to query. Right, so that's Parquet. What that is, it's a fast columnar file format. We could talk about that a bit. You also have to have some format that you are actually going to process the data with, right? Like so, when you actually do the calculations to do string manipulation or do arithmetic operations or group or whatever, like you need to have a representation in memory that's efficient for processing. So that's what Arrow is. It's the memory format. Along with
this is where you not just store the data in memory, but you store it in a way that's aligned with CPU architectures.
That's right.
Yeah.
Which, roughly speaking, is typically columnar these days, right? So it sounds really silly, right? It's like, oh, instead of storing it in rows, we're going to store it in columns. But the reason it's so different is because modern CPUs are really good at doing the same thing over and over again, and they have lots of data parallel instructions. So if what you're doing is you're taking an array of like 8,000 elements and you're trying to add it to another array of 8,000 elements, computers have very high performance instructions that can do that. They do like 6 or 8 or 16 integers in each cycle, right, with these big SIMD instructions. And compilers are very good at auto vectorizing, aka generating code that uses those instructions if you've got the inner loops right. So basically, by organizing your code, rather than be like, we're going to do this calculation for this row, and then we're going to do then just move one row after another. If instead you do like, we're going to do 8,000 of the same thing all at once, picking 8,000 because that's a common batch size, but like it's several thousand is basically the pattern. The CPU just gets going and it just rips it through, and it goes 4 or 8 times faster.
Yeah, this is one of those things where, in theory, there's no difference between processing it by row and column, but in practice, there's a huge one, right?
Huge difference. Huge difference. That's right.
Okay, so that takes us to Arrow.
Right, so that's what Arrow is.
Yeah.
And then, right, so now you've got some way to process. But it's actually somewhat of a pain to work with these columnar formats because it's not like everything has to be columnar based, and it's not like you can just run SQL. So now you need an actual engine that can run SQL. As an example, but there's other pieces too, even if it wasn't SQL. So that's what DataFusion is. So DataFusion has a SQL parser, and it has a planner and an optimizer and a fast execution engine, right? So basically, with I think 3 or 4 lines of Rust code, some of which are just like adding something to a cargo file, you can basically have like a fast embedded SQL engine for your own project, right? And so you might argue, well, you could do that with DuckDB too, which you can. By the way, DuckDB and DataFusion are approximately the same performance. The difference in DataFusion is it has extension APIs basically anywhere for you to plug in. So you can, all the different functions, you can override them or add your own functions, right? Those are classic things. But you can also add your own plan nodes. And you might ask why you want to do that. For example, if you wanted to build a new query language, right, because you don't like SQL and you're part of the 50 years of people who are trying to do better. But think about that, right? Like there might very well be a successor to SQL, but right now, or at least before something like DataFusion, if you wanted to build your own query engine, but like if you want to produce a new query language, you basically had two choices. You could either write the whole engine yourself, right, which takes a lot of effort, or you could, I don't know, try to transpile it to SQL or something like that. Right? Those are the two common approaches. And it's transpiling to SQL means you're basically restricted in your language to whatever you can express in SQL, even if you're transpiling it. And if you build your own engine, then it's this huge effort, right? You've got to build intermediate representations for the plans on all the optimizers that do all sorts of stuff. And so
I can imagine, you heard of Datalog?
I've not heard of Datalog. No.
Datalog is this interesting not SQL query language that has some interesting features, like it's really composable. Right?
Yes.
And in the back of my mind, I've toyed with the idea of creating something that uses Datalog. There are a couple of databases that do, but I've toyed with the idea of creating one. And like you say, it's way too much work because you don't just create the language.
Yeah.
To build the database.
So I love to think about it as like LLVM as is my personal favorite analogy. Okay. So here it is, right? Like LLVM, I know is like a pretty low level thing. Not everyone gets it, but so LLVM is the suite of compiler tools that underlie basically all modern programming languages, right? So you Clang, Swift, Java, probably Julia. I don't actually know it. Zig. All of them use, they have their front end, they have the language, but actually when it gets to the time to like generating optimized code for particular architectures, they all, and like the debugger support, they all use LLVM, right? And so I think the parallel there is if you want to build a whole new language today, rewind the clock to the late 90s, whatever. You want to build a new programming language, early 2000s maybe. If you wanted to build a new programming language to compete with GCC, which was like the top dog then, right? Because that's basically the best compiler. You either had to build it proprietary, so which if you were Intel you could do it, but not many other people did, or you're basically stuck. And the reason you were stuck is because it wasn't just you had to make a better like C compiler, right? You had to implement all the basic compiler optimizations and then the code generator, right, to make good code for a particular architecture, and the debugger, right, and the other tool support and all that stuff. And so if people wanted to innovate in the language design, right, like, hey, I don't want to deal with C anymore, like Rust, like I doubt Rust ever would have been able to get around if they had to both innovate at the language, but then also re-implement all the low-level optimizations, code generator, debugger, all that stuff.
Yeah.
Right. Instead, they could focus all their innovation on stuff that they cared about, and they could use this high-quality shared foundation under the covers.
Is this how most of the projects using DataFusion break down then? They have one big insight about performance and the rest is user space? That's probably an oversimplification.
Well, I think it's more like, well, we should probably talk about a bunch of the interesting stuff people do with DataFusion. But like, if you're going to build a database, which is a very common thing to do with DataFusion, I think people they'll often like they want SQL, right? But then they have different ideas about maybe how the data gets into the database. Like either like in the case of my employer InfluxDB, the data actually doesn't come in as tabular data. It comes in a semi-CSV final format called line protocol, which is fine, right? But then we turn it internally into stuff. And so from the end user's perspective, like it's you're inserting line protocol and you can query with either SQL or actually we've also implemented a language called InfluxQL, which is kind of like SQL, but much more focused for time series. And that also runs through DataFusion. So the point is we could build this whole system, right? We didn't worry about the low level implementation. Well, I mean, I worried, but most of the people working on Influx didn't worry a whole lot about how like the low level of DataFusion was working. Instead, they were focused on the features or whatever that were important for our users, right? So ingest, how the data is reorganized and managed in its life cycle over time and that sort of stuff. Yeah.
Okay, so maybe we should take that as an example then. A time series database.
Yeah.
I would have thought, just naively, I'm building a time series database. I take most of it from DataFusion, so I'm not worrying about parsers or storing it on disk. I've got to write custom indexes, I would guess is the first problem that's mine to worry about.
Custom indexes and or the ingest pipeline is probably the thing you need to worry about the most, right? When your data comes in, a time series database typically has to get it organized as quickly as possible into a format for querying, right? So that's one major challenge of a time series database. Another major challenge is managing the data and during its life cycle, because often time series databases like ingest huge volumes of data, like influx. I'm talking about in general, but influx specifically. But a lot of that data is not like, it's really valuable for when it's new, right? Like what happened in your monitoring is very, very important to be able to quickly query it for the last half an hour, a couple of days, whatever. But by the time it's like a year old, it's much, much less valuable. And so the amount of like resources you want to devote to managing and querying and whatever the data that's really new and the data that's really old is very, very different. And so a lot of the sort of techniques of building a time series database is how do you manage the data as it flows from being really hot and really important to query super fast to not as important, to like then eventually you got to age it out, but maybe you want to do historical analysis on it for machine learning or whatever type AI, maybe I should call it now, but like, that kind of workload in the future. So that sort of managing the life cycle is typically what you'd probably spend your time on now, rather than like reinventing that query engine.
Right. Yeah. I'm trying to imagine how that would fit into DataFusion. How much of that am I just doing on disk myself and just feeding it into a query engine, which is DataFusion? Give me the border of what DataFusion does and doesn't do in a project like that.
Yeah, well, so let's say you already had data on disk in a format that DataFusion comes with native support for, like Parquet is the classic example. But there's also, it supports JSON and CSV and Arrow and Avro, I think, are the data sources that come built in or provided with the Great. But you can use the same APIs that those use to implement your own. But let's say it was in one of those formats. What you would do is you tell DataFusion which files formed what table, right? And then you could, that's actually enough for people to immediately start querying the data, right? You say, my measurements table lives in these sets of files. You register that with DataFusion as a table provider, and then DataFusion will go through the trouble when someone goes and writes a query that's like, whatever, compute the average CPU usage over the last 5 days or whatever, bin by minute, right? Like all that machinery that's required to run that query will be run through DataFusion, right? So the SQL, it'll parse SQL, it'll produce a AST that'll then be translated into what's called a logical plan in DataFusion, but that's the traditional way in a database engine. You'll have a plan that represents the relational operators that compute the results you want. Then there's like another whole level of a bunch of optimizations happen on that logical plan. The optimizations are effectively rewrites that produce the same results, but do so hopefully faster. And it does things like partially evaluate expressions and remove joins when it can, and a bunch of stuff like that. And then it'll apply yet another whole set of optimizations, which would be like, it'll translate it to a lower level form called a physical plan, which is called an execution plan in DataFusion, but it's like a much lower level detail, and it has particular, it knows exactly what files are being scanned, and it knows how the data is sorted and which algorithms it's going to use to do joins or grouping or whatever. And then that will then get run. That plan gets run by the DataFusion execution engine, which has all sorts of like low level optimizations to do that byte pushing really fast, right? It knows how to read Parquet super fast. It'll push predicates down into the scans. It'll only read columns you care about. It'll apply limits where it's necessary. Like there's all sorts of stuff we could talk about like endlessly, which are basically all well-known techniques. And what I just described, by the way, is like how pretty much every database engine is implemented. It's not, or at least the classic ones. So DataFusion is not trying to break new ground with some innovative design, right? It's trying to be like a really solid industrial foundation that implements best practice, but it's not implementing the latest, greatest crazy research ideas in hopes that those will pay off. Like we're trying to do tried and true.
Right. Okay, so I'm forming a mental picture where actually the thing that's coming to mind is Postgres. When I go to Postgres and I type explain query, and it spits out a whole bunch of stuff that says I'm going to do a hash join against this table with a cost estimate of that.
Yep.
That story from query to this is how I will go to disk and fetch individual bytes and join them together, that's DataFusion.
Yeah. Not just the story of how I'm going to do it, but then all the code to do it. Right.
Yeah. Okay, so maybe we should talk about how you hook into that, because let's come back to indexes and optimization. I want to hook in because I start off with naive implementation and I realize I can easily write a specialized index. So how do I teach DataFusion to consider my index when it's optimizing the plan?
So the first thing, let's take a specific example of, let's say you could, I don't know, you're trying to write something which knows how to look up very particular, I don't know. Do you have an example of an index you want to fire up, or I can make up one too?
Okay, let me think.
What kind of query you care about?
No, I'm going to let you give me an example. I bet you've got a good one.
All right, yeah. So I have some good ones from time series. So, let's for example say that you have, you might imagine it's really, really important to get the most recent value really quickly, right? Like, you got a table, it's getting data in, but it's very common to be like, what's the current sensor reading, right? So you want that to be super
let's
fast.
go with that. Let's say I've got everything on disk, but the latest hour of data I keep deliberately in memory.
Right, deliberately keep in memory. So what you could do, by the way, this is exactly what Influx does, is we have a special table provider, which is the interface in DataFusion, right? So DataFusion comes with a table provider that knows how to read Parquet files out of directories, but you can build your own and using much of the same infrastructure. So what you could do is you could build a table provider. So from DataFusion's perspective, it just looks like a table, right? That you can tell it what you have to tell DataFusion what the schema is and whether the provider supports predicate pushdown. It can apply filters during the scan, that kind of stuff. And then when it goes to the planning time, eventually DataFusion will say, hey, all right, I want to run, I want to scan this table with these set of predicates and this push down and these columns. And you, table provider, please give me the specific plan to execute. And so what you do in the case of like you had the last hour is your logic would look at the predicates that came down, and maybe you'd have a predicate on the predicate is just a fancy way of saying like a Boolean expression, right? So it's like that filters out rows. They're really common in databases. So you would use those predicates and you'd figure out, well, hey, this query is only looking for the last 30 minutes of data, right? And DataFusion did all the trouble to figure out that those predicates applied to your table. So you didn't have to do anything. You just look at the expressions that came down. You say, hey, I know it's 30 and I look at, and I know I have all that data in memory. So I'm just literally going to take the memory chunks in arrow right there and store them in arrow. And I'm just going to pass those directly back to the scan for DataFusion. And that's basically all you got to do, right? You don't have to do anything grouping. DataFusion will do all the push down stuff.
Okay. What if my query is looking at the whole day, but my data, I can say I can supply the first hour quickly. How does it handle, I get some data from this table and some data from that table?
Well, it depends on how you model it, but if you modeled it as though it were a single table, to DataFusion's perspective, it would just say, give me a scan. But what you as the implementer would do, you would provide a plan. This is actually exactly what InfluxDB IOX does, which is InfluxDB 3. It'll basically give you back not just a single thing that knows how to scan Parquet files, but in our case, it would give you back the thing that knows how to scan Parquet files that have the historical data, and then a thing that knows how to provide the data for the most recent information, and you basically union them together. So from the DataFusion planning perspective, it has no idea that they're coming from different sources until it gets to the physical planning time where it effectively would compile the access to a table into actual operators that know how to fetch the data. And then some other optimizations might go on.
So I sort of create a hybrid aggregate table, and when I'm asked for logical searches, I give back some physical details. Okay.
Yes.
I'm with you.
That's one way to do it, for sure.
Okay. Okay. I can just about see how that works. I want to talk about extending the language, but I've got one quick question.
Yeah.
Since we're talking about live data, I query through the last 24 hours of data and aggregate it out, and I get a result, right? That has 5 different continents and the sales totals for them.
Yeah.
Right?
Yeah.
Now, 5 minutes later, I've got some extra data. Is there a way to mix that in? Is there a way to say, well, I had the state of the query here. Can I add in a couple of extra rows and see what would have happened?
Not in the core of DataFusion. Like what you've just described is often implemented as, at least I think would be implemented as materialized views, right? Or like streaming queries or something. Well, actually, streaming queries is another way of doing it. But like a materialized view is the classic way of, you have like a query that you've defined up front, right? Is the view definition. And then there's at least two ways to execute that, right? One is you just re-execute the query every time someone wants the results. And another way is that you can incrementally update. You can basically store the result of running that query previously and basically incrementally update that result. So that's called incremental materialized view maintenance, if you want to get exciting and like read a bunch of research papers about that. Yeah. So there are people who have implemented that using DataFusion, right? So they basically have their own query rewriter that knows how to look at a query, figure out when it can combine new data with a historical pre-computed. I think there's a company called Polygon that they gave a talk last year in New York about some of the cool ways they've implemented materialized views. But yeah, so I've seen people do it with DataFusion, but that's not directly built into the engine itself.
Okay, I'm gradually starting to get a sense of where the boundaries lie, which is interesting.
Another thing that people did that I didn't expect when I first started working on DataFusion was they've implemented like streaming SQL systems. And so like I wasn't even super familiar with what those are to begin with, right? Mm-hmm. So Flink is the canonical streaming SQL system, Apache Flink. So at a high level, like traditional databases or, like old school analytic database, you go and like you run a query and you get a result, right? And the engine's all designed to really crunch the data fast, and it can basically, whatever query you give it, it'll come up with a plan for it. It'll give you the answer. Streaming SQL is a little different, where you basically create a standing query up front. It's kind of like a materialized view, except the difference is as data flows into the system, the standing query will continually compute like an ongoing operation. So like, for example, maybe you're computing what's the average stock price for every minute interval, right? So basically, as the stock price stuff comes in, you're keeping an average, and then once the time boundary turns over to the next minute, it like emits the output. So those are called streaming SQL queries. I'm sure it's far more complicated than I just did, and I didn't do it justice. But that's like really simple example.
Yeah, it's good stuff.
And it's kind of interesting. DataFusion, I thought, was sort of a classic batch processing system where you just give it some arbitrary query and it'll just crank on it. But it turns out a bunch of people cared about implementing these streaming systems, and they've put a bunch of features in DataFusion to help support that, specifically the analysis to know what queries can be streamed and what can't. And so now there's several people who, several companies like Sonata and Arroyo or two, and I'm sure there's other ones that are coming up that have this sort of streaming SQL engines that are built on top of DataFusion. It's been pretty.
That's cool, and it's cool that you didn't see it coming, but it was still enabled.
Yeah. I think it's partly because like DataFusion also has what's called a streaming execution engine, which is, if you think about what a database execution plan is really doing, right? Like it's often described using fancy words like relational operators or whatever, but like logically what it is it's a data flow graph, and what's flowing, like, so that means there's nodes and edges, right, that are connected, and data typically flows from sources like reading data off disk or whatever or other access paths, and it flows eventually, like the sink of the graph is the client or wherever the data is going. And then, so what an execution engine really is just like a data flow engine that's driving this graph. So like a relational operator is a very fancy way of saying what's going along logically on those edges are tables, right? They're not just single values. They're like rows and columns. And so with that as a model, if you're not, like the simple thing to do that you might do initially is you just like, well, I'll just compute the whole intermediate result, right? So you literally compute all the data that comes out of your file, and then you pass that to the next thing, then the next thing. But as you might imagine, for large data sets, that's very, very RAM intensive because you have to like store it all in RAM, right?
Yeah, and needlessly slow because you have to finish processing 1 million rows before you can take it to the next step.
That's right. And so best practice in these analytic engines is to implement them as streaming engines, right? So you still are passing logically these relations around, but what really happens is you pass like batches of rows. So instead of like if you've got a million rows that come from one to another, you're actually like what you do is you pass the first 8,000 or 10,000.
I knew you were going to say 8,000.
8,000 is my favorite number. There's research papers, if you want, we can go, I can put them in the liner notes, but like the research papers basically show somewhere between 4,000 and 16,000 rows in the batch work approximately the same, right? And exactly where in that. If you get too much bigger, the rows stop fitting in L1 cache. So that's not effective. And if you're small, if you're lower than that, the overhead of like the per batch overhead starts becoming a significant factor, right? So you can't amortize the per batch overhead as much. So like 8,000 is right in the sweet spot.
Current sweet spot.
That's the current sweet spot.
Okay.
Okay.
So you batch up your million rows.
Oh yeah. Sorry, back to the million row thing.
Yeah, you batch up your million rows into 8,000 size chunks and just pass those.
And so that's called like I would call that a streaming engine or a streaming execution engine. I think that's pretty typical these days for analytic systems, because otherwise, if you try to process big data, you just run out like data that's larger than RAM. It just runs out of space.
Plus, it must also open up the possibility of doing it like multi-threaded, right? That must get easier.
Yes. Oh, well, there's an awful lot of effort that goes into making these engines multi-threaded for sure. Although I think technically speaking, you can have a entirely in-memory engine that's still multi-threaded, but realistically, in fact, I think the research system Umbra is like that. But anyway, that's probably less interesting. So yes, there's actually a whole lot of effort that's gone into applying multiple cores, keeping them all busy all the time to running plans. And that's another thing, right? Like you take my Mac laptop and I go run some query, it'll like keep all the cores busy, which is very satisfying. But it takes a lot of time and effort to like get that to exactly work right and not to have bottlenecks and not to have deadlocks and all that sort of stuff.
Is that kind of thing planned out ahead of time, or is it dynamic? Does it start rerouting around different CPUs?
Well, DataFusion uses something which I would call a classic Volcano style optimizer. So like if you read the data, if you're a database literature weenie, that you know what that is, which I assume not many people.
I've not heard. I love the term. I want to unpack.
Yeah, so the name Volcano comes from or maybe it's Volcano comes from a paper about a research system called the Volcano system by Guts Graf, I believe, back in the day. But at a high level, what that does is the plan is divided into some number of like subparts, and each subpart runs on a single core. And then there's only certain parts of the plan where the data is transferred back and forth between cores. So in the original Volcano paper, it was called, I believe those operators were called exchange operators. But the Volcano paper describes how you would take an engine that was designed for one core and run it on multiple cores. So anyway, this exchange model is common. I want to get to a big discussion because there was a big debate a couple of years ago about whether that's a good model or whether we need a different model. But I'm going to postpone that for just a moment. So the way like, let's take an example where if you're trying to just aggregate a bunch of data, and maybe this will be a good example to give you and your listeners some sense of like what's actually required to implement fast aggregation. So when I say aggregation, I mean like I have 1 billion customers and I want to find the average, or I have 1 billion transactions or whatever in a database, and I'm trying to like find the average value of the transaction for every customer, right? So logically, what that means, like if you wrote that in a Python program or whatever, you'd probably you'd read the data in, you'd build a hash dictionary keyed on customer, right? And as every row came in, you would look up the customer record and update the running average or whatever, right?
Yeah.
So that's basically how, and so databases do it like that too, except they do it very fast and they do it with all the cores. And the typical way to do it is you use it's called a multi-phase aggregation. So instead of having just one core sitting there, like looking at every customer, what you actually do is you start immediately, you'll have two phases. You'll actually have two sets of aggregation operations. The first one will, at the core, they all do that. They have a little hash table that they update. Although, the details of how to do that fast is also fascinating in and of itself. But at the high level, what you do is you arrange your plan so that every core sort of like reads a block of data out of disk, right? Like filters it or whatever, and then immediately aggregates that block that it read. So all cores are basically going at once, reading data, aggregating, and they're not talking to each other. So that part's really fast. Yeah.
Right. And there's some part of the plan that says, okay, core 1, you've got this byte range in the file. Core 2, you've got this byte range.
Yes. Yeah. Yeah. Okay. So that's how DataFusion's planner handles that particular thing. There's other techniques of how to do it, but at the end of the day, something basically assigns different parts of the file to different threads, and those threads like are purposely designed. They go read the data off disk as really as fast as they can, and then they aggregate it immediately after they read it off, and that's important so the data basically stays hot in the cache and never, like you don't want to like read a bunch of data, buffer it somewhere, then eventually get around to aggregating it. To make it really fast, you need to like read it, aggregate it immediately, and then go try again. Then just do that in. But if you do that operation, right, so that's great. You keep all your cores busy, but now you like, let's say you have 16 cores, you now have 16 hash tables, right, that all could have, every customer could be in every one of those hash tables or some subset. You have no idea. So then the way these fast analytic engines will work is that what you'll do is they'll then effectively shuffle the contents of the hash tables across all the cores. So typically what you do,
yeah. So I send all the ones beginning with A to core 1, and all the ones beginning with B to okay.
That's exactly right. And then, but of course, there might be duplicates because they might have come from different original cores, right? So then you have to do a second phase of aggregation to compute the final result.
Right. Yeah, and then presumably there's a third phase where you stick it all back in one place to be served up.
Depending on what you want, like. If you're just streaming out the results, like they can each kind of just start sending them out and you can just read them back. If you want the customers, like, I don't know, ordered by a particular, like by last name, for example, you would then have to sort them somehow.
Okay. Yeah, that makes sense. I'm wondering how this is implemented, because I know DataFusion's written in Rust.
Oh, yeah.
Under the hood, is this like all asynchronous Rust or something? We
do use asynchronous Rust. I would like to talk about that as a separate topic too, before I talk about in terms of Rust and performance stuff, right? Like traditionally in databases, I have a particular period, but like traditional databases, you would write them basically in C++, right? That was the way people wrote databases, and the story was you basically had to write it in C or C++ to get good performance, or get good, because JVM could get you so far, but at some point, basically, you needed control over memory, and you just can't do it with the JVM. That's like the traditional. If you go ask the database purists or the researchers what the story is. Now, however, you might observe that like 15 years ago or 10 years ago, there's a huge push into Java anyway, right? There's a whole like generation of systems that were all database systems that were implemented in Java. Like I'm looking at Hadoop, right? And a bunch of those other, Spark is another good example, right? It was basically written in Java. At least at first. And my theory is that the reason that is because despite the fact that you leave some performance on the table, you're just so much more productive as a programmer. And I know it's like productivity is kind of like a weird generic thing to talk about, but like as a personal anecdote about productivity, right, as a C++ programmer, the things I didn't have to do in Java, and I'll talk about Rust in just a second, is like, why, after 2 days of really hard beating, does the program segfault, right? Like, why does it crash?
Yeah.
I don't know, right? And you spend like forever trying to debug why, like whatever the particular memory race or stomp was, right? So productivity is not just like how fast can I pound it out in the editor. It's like how fast or how much efforts you have to do to make a real high quality production piece of programming, right?
Yeah. And how much of next month will I spend tracking down segfaults is a big issue.
I don't want to admit how much of my time in my previous, my earlier career I spent chasing down like weird. It would be like, hey, we'd beat, I still remember at Vertica, we'd have this like stress test that we'd run for 2 weeks on the database. And like what would happen is after 2 weeks of like basically doing random things to the database, it would segfault. Right. And then the goal would be like, all right, you got to go figure out where the bug is. Right. It'd be like, like you can do it, but it takes a long, long time.
Yeah. And in the worst case, it takes you 2 weeks to check that it actually worked, right?
Oh yeah. And then you got to restart it, right? That's exactly right.
Yeah.
Well, and with still one of the other great cases there was we had one of these things that seg faulted, and we spent weeks trying to figure it out. And eventually what happened was it turned out the hardware was bad, right? There was like RAM in one of the servers that actually was like crappy and would every now and again flip bits. But like proving that was the problem was like a multi-week endeavor. So anyway, that's like a lot of words to talk about the productivity of C++. Oh, by the way, also I don't know if everyone who listening here has ever messed around with C++. You ever like get weird linker errors? Like, why does it can't find the stupid symbol, right? Like in which WL command you have to give it to like make it find it. I wasted not as much as chasing down distributed crashing stuff, but like far more time on the build system crap than I would like to admit either. So anyway, my thesis here, right, is that Rust basically, it's basically as fast as C++. We can argue whether there's cases, but it's basically as fast, and it's very, very close to the Java productivity, right? Like in my what is now 5 years of professional Rust development experience, there's been like one memory problem, depending on how you count, like one weird memory crash. Now that came with a lot of like, a lot of frustration with the Rust compiler at first, for sure. Right, because the compiler's just like, I'm not letting you do that. And I still remember at first I was like, I've done this for like 10 years in C++. Just do what I'm telling you. Like, no, I'm not going to do it.
Yeah.
and then eventually you understand, like, okay, eventually you understand, okay, what it's basically preventing, like eventually you really appreciate why it's not letting you do things. But at first it was super frustrating. But anyway, so where I'm headed with is, yes, like DataFusion is all written in Rust. There's very little unsafe. There's some places that use unsafe, like the really low level kernels sometimes do, often to like skip validating that something's valid UTF-8 or whatever, when because you wrote it in as valid UTF-8. But I mean, the amount of effort that's gone into like, obsessing about not copying strings around and not avoiding copies and being clever about things is like, it's a lot. There's been a lot of people obsessing about that level of stuff. And so like the DataFusion aggregation is really, really fast. And filtering and reading Parquet is basically state of the art. From what I can tell, I don't know anything that goes faster. So I'm quite pleased with what we've been able to do as like a bunch of random people on the internet hacking together, right? If you ever told me when we started that we'd be able to build like, I've been in enterprise software for 20 years, so I know what it's like to build with that in big teams. And like, if you ever told me we could build the level of technology we have, right, as an open source project with just random people on the internet who I have no idea where they come from or what their backgrounds are or why they're doing it, it's like, I would have said you were crazy when I started. But here we are. It's been super awesome.
I want to get into the project organization, but I still want to know before we go there. I still want to know what Rusty techniques you're using to manage multiple cores and dispatching data between them in a pipeline.
All right. The short answer is we use async Rust and we use the Tokyo runtime.
Okay.
And the reason I wanted to postpone that before is because I think I personally, maybe I treat it a little too personally, but we've taken a lot of heat in the project for that decision. I think it's the best one we ever made, in my opinion. But not everyone's agreed. So I just want to acknowledge that not everyone thinks it's a great idea. However, I think it's a great idea. And the reason I think it's a great idea is I have a blog post about this. Maybe we can point about it, but
I'll put it in the show notes.
I have written my own thread scheduler. It's really hard to get, like, it's easy to get it to work 99.9% of the time. And it's really, really hard to get it to work all the other time, like the final 1% of the time or 0.5% of the time.
Yeah, I can believe it's full of corner cases.
And it's full of crazy corner, especially shutdown and canceling and all that nonsense. And Tokyo is really, really good, right? Like I know people talk about, but not just as an async IO, like actually doing, I understand it was designed for IO and blah, 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 blah. And DataFusion absolutely fills it full of CPU bound work. Like there's a whole thing about whether that was a good idea or not. But it's a good idea. And the reason is because, one, you get access to the super high quality thread scheduler, which is Tokyo's runtime. Another thing is because you get basically built-in language support for implementing what I would call continuations. Is what we call that. But it's like when you're building one of these data flow engines, what you have to do is you have to like you do some work, and then eventually you need input or you need to produce output. And when at those particular junctures, sometimes you have to either wait for more input to be available from your input, or like the output's not ready to consume what you're ready to produce, right?
Yeah.
So what that means as a programmer is that you have to be prepared to like basically return control back to the thread scheduler at those junctures.
Yes. You want to model the whole
Right.
thing as a bunch of coroutines that can wait on data and ship data out.
Well, that's one way to implement it, is as explicit coroutines, for example. However, Rust asynchronous, right? The thing is, the compiler builds that stuff for you with async, right? Like, so every time you do a .await in Rust, under the covers, like with some crazy, I don't even know how it's implemented in the Rust compiler. Effectively, what that does is that produces something which returns control, like literally like return, right, to the Tokyo scheduler, which can then call you back directly, or maybe it'll call something else. But the point is, you as a programmer just write straight line code and like, oh, I need some more data. All right, I get it. .await, and then I continue, right? So the code is very clear what it's doing. It doesn't have to be like, oh, I need more data. Oh crap, I gotta save all my state in like some variable somewhere, return control, and then next time I get called, come back and have to pick up where I left off.
Yeah.
Like the compiler does that for you.
Anyone who's spent time in early JavaScript in callback hell and then got syntactic sugar for async await, right, knows the value of that.
Yeah, well, I mean, and my experience with something like that was in like it was an embedded, it was like an embedded network device in 2004 or something, and a company called Data Power. But like we had the same thing where we had a multi-threaded execution engine. This was all C, by the way, C++. But it was very important. Since it was a network device, it was doing lots of I/O, and so you couldn't do blocking I/O, right? You couldn't issue blocking I/O calls. But so when you were in the middle of processing something, if you want to do an I/O, you basically had to save everything you were doing in some structure and then like register a callback to get called when the I/O is ready, and then return back to the kernel basically. And like,
right, yeah,
the number of bugs I spent chasing down were like, getting it work the positive way was annoying, but it was like fine, right? But like the error paths were just like a giant, like I was like, oh, I was halfway through something errored. Well, you have an error callback, but the like, oh my god, it was miserable. So
clearly triggering some trauma for you here.
Yeah, right. And so then you see this compiler doing it, and you're like, this is the best thing ever, right? The compiler does it. Yes, sometimes it doesn't get the lifetimes right. Yes, some people don't, like has some overhead or something at runtime, but like compared, like, I don't know, compared to doing it all yourself, it's so much better to have the compiler do it. And like I said, there's definitely people with different opinions about it than me, but like I would use Tokyo for run CPU bound work again in a heartbeat.
Okay.
In fact, I did. I'm working on like with some other guys. My personal passion project at the moment is building like a TPCH data generator that just goes like fast. If you ever try to generate, TPCH is like a classic analytics benchmark, and it's models like orders and stuff. It's very well, like, because it's easy to generate the data, it's super well studied. And so basically every analytics system will like post numbers about the TPCH benchmark. But the data generator is terrible for it. It's like vintage 15-year-old C code that like takes forever to run, and it's miserable. And it makes something that's kind of like CSV, but not really, because it's stupid. And so anyway, one of the things we've been doing is trying to like make it fast. And so I've currently got it. We've got it cranking. Anyway, we got the data generator going super fast, and I absolutely use Tokyo to use CPU bound work, and it's like like 20 lines of code, and the thing's like cranking through all the CPU. It's like amazing. Anyway, that's a preview of coming attractions. That's gonna be great.
This is good to hear, because I'm working on a Rust side project myself, and I picked Tokyo because it seemed like the default. I'm glad to see there's a good review on it. I've made the right choice.
Now, the one thing that legitimately is tricky is if you do CPU bound work on the same Tokyo runtime as you do I/O, like DataFusion, it's very easy to do that with DataFusion if you're not careful. And frankly, for systems that you're doing a few queries, it doesn't frankly really matter all that much. But if you care a lot about latency, especially with there's like large numbers of queries per second, you really don't want to be doing CPU bound work on the same Tokyo runtime as you're doing your network requests, because basically the network's calls are not being serviced quickly enough, and so you end up getting throttled by the network layer. So I will
So what
say
do you
it's
do?
like, if
Do you have to run two different sets of the runtime at once?
yes, that's exactly right. And so
Is that
like
easy to
that's,
do?
and which is, it's not as easy as I would like it to be. We have,
Okay.
you can do it. Like we do it in Influx with a bunch of other people have done it with DataFusion. Like the Pydantic guys, for example, I know. Yes, it's not as easy to do. Like the upside of using just one Tokio thread pool is that it's very easy to get going, right? Like you basically don't have to think about it. You can immediately do IO in your table providers, right? Like this, it's just all works.
Mm.
The downside is if once you get to the point where you care about running large numbers of transactions a second, these like effects of running the same, like different types of work on the same thread pool become much more apparent. And at that point, it's a little tricky to fix. Although I still posit it's good that like many people never even get there, right? They never get to there, and so they don't have to worry about multiple thread pools at first. So in my opinion, it's a good trade-off. But
Right. Yeah.
not, if you spend 2 weeks trying to figure out why the hell it doesn't scale, under serious load, maybe you don't feel the same way. But that's okay.
Yeah.
So anyway, yeah. So traditionally, what you do in a network system that's also doing lots of CPU bound work is that you have separate thread pools. So that you have one thread pool that's handling the network requests, so that it can, with low latency, respond to whatever is coming into the network or whatever work the kernel has for it to do. And then you have the other threads cranking away, keeping the CPUs busy doing heavy data processing work. And you can
Yeah, that
definitely do
makes
that with
sense.
Tokio. Yeah. Sorry, go ahead.
It's almost like having, you sort of wish that was built in and you could have like different quality of service levels for different workloads. But what you're basically doing is adding that in manually.
Yeah. And I think part of it is that it's not always clear. Like there's a bunch of trade-offs involved, right? Like if you want to always ensure you have the lowest latency network response, you'll basically reserve a core or more for only doing network stuff, right?
Yeah.
But that'll look like, if you're under heavy CPU load, it'll basically look like you're not using all your cores, right? Because like some you're basically keeping some of the capacity around for if you're going to get additional network requests, which might be appropriate for your system, or it might be seen as not like something you don't want to do. So I think the exact sort of mix of how you want to assign your cores and whether you want to reserve space up front or whether you're trying to total maximize what you're currently doing, I'm not sure there's one generic way of doing that would
Right.
work
Yeah.
for everyone.
And that makes sense, going back into this idea that DataFusion is there for you to choose the parts you want, right? And build something unique, reusing the common stuff. Okay, I get that. So you've talked about how like Tokyo is slightly controversial. Let's talk about working with other people. How is Rust? How is DataFusion organized as a team? It's an open source Apache project, right?
The open source Apache project. So it's run. It's run the way, or it's governed the same way that every other Apache project is run. I don't know how familiar your listeners are with that. In my mind, Apache, like the Apache Software Foundation, doesn't directly develop any software. Like what I like to think about Apache is that it's a set of people and processes and like stuff that a open source project, like best practices that open source that they figured out work well for open source practices, and then they basically allow projects that want to participate and follow those guidelines to come be part of the umbrella. And so the Apache Software Foundation handles a bunch of stuff. Like there's some infrastructure stuff they handle, and they handle the governance and how it does. But mostly the projects at a day-to-day level, certainly the code or what goes in there, like all that's done entirely by the project itself, not by any sort of high-level Apache thing. So there's a PMC, which stands for Program Management Committee, Project Management Committee, something like that. And that's maybe 20 people, I think, on DataFusion, something like that, 15, 20 people. And then there's committers who can actively basically have write permissions to the repositories. And that's another, so there's probably 40 people in total across that.
That's very healthy, yeah.
Well, and like a lot of open source projects, some of them are not active anymore, but some of them are very active. And so the project, I don't know, has multiple commits a day, probably between 5 and 10 a day for the last 4 or 5 years now. So in terms of the number of like the last time I did numbers for a couple of releases ago, it was we do sort of monthly releases, and there were like on the order of I think it was 47. It might be more individual, like distinct committers for each one of those months. It might have been. It might have been 90. I should go check. But like the point is, there's a lot of individual committers. Now, like most open source projects, if you look at the distribution curve, it's like a power law curve, right? Like there's it's a couple of people who do a lot, and then there's like a very long tail of people who did like one thing.
Yeah.
But I think from my perspective, the health of the project is very, very good. Now, again, I'm super biased, right? Because like I spend a lot of time on there. But I mean, if you go there and you can look, right, there's multiple new PRs a day and tickets, and people are clearly using it for real issues in their or real systems because they're filing, crazy corner case bugs, right? Which I don't think you find and want to fix in your spare time.
Yeah.
So,
do you have the whole? Is there like a DataFusion improvement process? Official? Are there dips, numbered dips for?
No, there's nothing formal like that. So there are some. One of the weirdest things for me starting to work on open source, and so I came from enterprise software background, right? Like literally I've been doing enterprise infrastructure software for 20 years. There was like, well, people were like, well, what's the roadmap? Who sets the priorities for these things? And it's like, I don't know, because there's no one that I know that is paid full time to work on DataFusion. Or even though it looks like I get paid full time, sometimes like I don't. I spend half my time in DataFusion maybe, and it's been my other. So no one gets paid directly, and there's no, like at a company, there's the company's sort of resources, aka the people and the time, and then there's a way for the company to kind of set a priority, right? And then there's like you kind of align the people to what the company's priorities are. In the open source world, there's like no equivalent corporate, like the Apache Software Foundation is certainly not setting it. The PMC is not setting it. The people who really set the agenda are the people who are providing the time to do the work. Right. So that was a really weird thing. Like, who's setting the priorities? Well, it's really the people who are going to do the work are going to set the priorities. So like you could say, we really should do whatever, but like if no one's going to do it, it doesn't really matter, right? And I have no direct control over what people do, or we can't. They're just doing it basically because they find value in it.
There's a question I reckon I could ask 1,000 developers and get 1,000 different answers. But how do you feel about that way of organizing a project?
I think it's worked out phenomenally well. That's what I think. There are definitely times when I wish desperately I could just be like, I want this thing done. You just go do it, right? Although it turns out, which when you're a manager in a company, you can perhaps do something like that. Although good managers, of course, realize that's probably one of the least effective ways to get people to do stuff. No, so what I've taken to doing, which has worked super well too, is I basically think about it as like the goal is to make what I want, what I think is the priority. Like I can't tell people what to do, I have no direct influence over them. But what I can do is I can make it easy. The easy path is for them to do what I think is important, or like the stuff I think is priorities for the project. So that's the technique I've been using, and I find it very, very effective. Now, what does that actually mean? It means spending a lot of time writing down tickets and explanations, and basically watching around. If you see someone who's like doing if you see someone who will show up to the project that's clearly like high caliber and is motivated, is going to do a lot of good work. If you see them show up and they have interest in some project where like I think is important, spilling to disk is a good example, right? Or like someone got excited about doing explain plans, which I can talk about, right? So those are recent examples. This TPCH data generator is another one where someone showed up that was interested in doing that. So, and I thought those were important too. So what I can do is I can I can explain what I think is needed or what I think would make a good project. Turns out developers love coding stuff, less defining projects, right?
Yeah.
And help review their PRs quickly and help make a big, publicize what they're doing. And so I think that's worked out really well from if I want stuff done, but I have no direct influence over people, making it like, hey, here's all this cool stuff you could do if you want to come work with us. It's been shockingly effective.
I remember we had Alice Cecile on talking about Bevy, and that really rings a bell. She was very simple, like talk about what needs working on, and people will organize around it.
I can't, like, I mean, I'll give you some examples. I will certainly admit that. So DuckDB is another one of these embedded databases, right? It's very popular. I sometimes have envy of DuckDB's feature set for a bunch of reasons.
Okay.
And one of the features they have that's really, really cool that actually is these explain plans, right? Those classic explain plans in a database look like the Postgres style, where they've got some indented text and they're kind of a pain to read. You kind of like got to have a special skill to read.
And it's the thing you call up when it's not performing the way you thought it was going.
Yeah, and it's like, and so for developers who understand the internals, like the explain plans are fine, like they have all the details you need. But if you're not used to seeing that, like understanding how to map that tree structure to like the actual, like the indents into a tree in your mind and doing that, like it's so anyway. DuckDB has this really cool, like basically ASCII art tree explain plan mode, and people love it. And I've wanted it for DataFusion for a while. And one of the CMU classes said, "Oh, one of the reasons we used one of the first projects we used DuckDB instead of DataFusion is because it had these cool explain plans, because it's easier. It's like a lower barrier to entry." I was like, "Oh, that's just annoying." So anyway, I wrote that up and we talked about it. And so someone who I don't even know what their real name is, to be honest. I know their GitHub username is Irene J. Thank you, Irene J. Showed up and was like, "Hey, this is great," right? So that person went and ported a bunch of the code from like the DuckDB rendering engine into Rust, put it in DataFusion. I didn't set like, and it was good enough that we merged it, and then we organized a project where we kind of like listed out, hey, we got to like port these different, there's like 20 different operators that have to be changed to use this new format. And we basically did one or two of them together closely. We figured out the pattern, and then we filed the other 18 tickets that's like, apply this pattern to this operator. And like in a week and a half, it was done. And like we're in the process. It's amazing.
And was your involvement in that, I mean, at the start, did you basically just draw out the ASCII art of what you hoped it would end up looking like?
Well, someone had filed the ticket about like, hey, it would be great if we had DuckDB plans. I might have done that. But then, one of the things I think the DuckDB guys have been really good at is building mindshare in the research community. Probably it's because they came from the database research community and they're running around talking about it, right? So again, I got sort of envy there. Like, well, how can I make DataFusion more inviting as a research platform? Because I think that's another way to draw contributors back, right? If you look at like, how do we get the product to be the best you can possibly be? Well, you got to get good people to come in and help you do it together, right? So how do you do that? Graduate students do database research sounds like a pretty good set of people to encourage to help you. So
especially if they're sick of segfaults, right?
Right. Well, yeah, and you get the burst from like Rust being like, the hit. People do seem to be very excited about doing Rust, so that helps.
Yeah.
But there's another example too, where like someone's recently been working a lot on spill. Like when you're sorting data that doesn't fit in memory.
In that sense, yeah.
Right. So there's a whole like body of research about how you actually do that efficiently, and you have to spill it to disk and merge it and manage memory and blah blah blah. Like it's non-trivial to get working right or to get working well and fast. And so DataFusion had a basic version of that, but it wasn't really. It was, as people started clearly using it in production because they started finding tickets. It was not as high quality as some of the other pieces of DataFusion, but several people have showed up who are clearly very good engineers and who are actively trying to push that forward. And so even though that particular project's not a priority from like my employer, like Influx is, who's my employer, we don't have disks attached to our processing thing, so we don't spill, right? So it's like it's basically irrelevant for us, but it's important for a bunch of enough other users that I think it's worth helping. And plus, there's a bunch of people who are clearly very good and trying to push it, right? So it's one thing if you're like, well, I gotta, some random person off the internet, you gotta somehow get them up to speed to even understand why spilling and whatever is important, versus like you got people who clearly understand that and are actively willing and able to help push the thing forward. Like if you think about leverage, helping them achieve that goal is a very high leverage opportunity.
Yeah. Especially if they have read through all the papers that explain how you do this properly, right? And are keen to implement it. Yeah, I can totally see that. So as we're talking about developers, pull me back out into user developer space. Like I would like to understand. I'm probably not going to start reading a database paper and implementing new DataFusion features, but I am curious about how you might do simple things like add in a new SQL function, or more complex things like how I might add in data log as a new language? How does that work?
Yeah, so for new functions, there's a whole bunch of examples of how to do that, right? The API internally that's used for, DataFusion comes with, I don't know, 300, 400 implementations of functions. But the APIs that are used internally are exactly the same that you as a user can use. So there's basically like a whole wealth of both example implementations of functions plus like simple write-ups in the documentation and examples. So in terms of adding a new function, it's very, very straightforward. There's a whole bunch of examples. Implementing a new language is slightly more interesting. What you'd have to do a new language is you need a parser for your data log, right? So something that would take like a string that came in, and you have to typically the way you would do it is the string comes in, like it's just a string of bytes. You have to implement some sort of parser that parses that into a tree, like an abstract syntax tree is the fancy way of saying it, but it's like a structured representation of what you wrote in text. And then there's a translation steps that translates whatever the structured AST means into the first data flow graph. So in DataFusion's case, that means a logical plan. So you need something which.
How much does that logical plan look like parsed SQL?
I don't think it doesn't look like SQL. It looks more like a data frame. It looks much more like, scan this. It doesn't say what you want. It says the how. So it's like scan this table, right? And then sort it by this, and then apply these functions to it, and then maybe aggregate it like this in that order, right? So it's a specific order that is built up. And so that initial plan describes sort of the how to calculate whatever result you want. And then there's a whole bunch of like machinery that goes on to try to make that calculation really fast. But the logical plan, the initial logical plan describes the what, like the how to calculate initially.
Okay, so I've got string parse it to my AST, and I've got to turn that into something that could be an inefficient physical plan mentally.
Yeah, you don't have to worry. Like you could just scan all the columns, apply this filter here, do some, aggregate it like this, and done. Right? Okay. You don't have to worry about how can I push the filters down, or where do I not have to carry the columns through, and how do I avoid sorting that if it's already sorted, and all that kind of stuff like that.
Right. Yeah.
It describes what to do, and then there's a bunch of optimizers that will go and make it
I think
really
I
fast.
see more clearly why you think of this as being a bit like LLVM.
Yeah, if you just generate that logical plan, then there's a whole bunch of stuff that happens after that. Like you can get explain plan immediately out of it, for example, or you can go run it through this crazy multi-phase aggregation, whatever we were talking about. Like you as a language designer don't have to worry about that at all. You just say, I want it aggregated like this, right? And DataFusion goes and does its thing.
Nice. And for the simpler case where I'm just adding functions to SQL, I've done this there was a Java-based tool that was looking there was SQL for the Kafka world.
Yep.
And a lot of it boiled down to there are simple scalar functions, which is I'll give you a value, give me the changed value back. And then there are aggregate functions, which are I'll give you the state so far and the new value and aggregate them. Is it just as simple as that?
Pretty much. DataFusion actually has four different types of user-defined functions. There's the scalar functions that you defined, that you described, which logically you get one row in and you generate one row out for each one of the input rows. There's aggregate functions, which you get given a bunch of rows for a group and you produce one row out. This is logically. Yeah. Then there's window functions, which are SQL window functions, right? Which like you get a bunch of rows in and you still produce a bunch of rows out, but you can look at the other input rows. And then there's also table functions, which basically you, in theory, get a table in and you produce a table out. So there's basically Rust APIs to implement all those different kinds. And they're all implemented in terms of Arrow, like Apache Arrow. So when you implement a scalar function, there is like a wrapper that you can literally implement like one row to one row. But the way most people will do it is the API is in terms of you get given a batch, my 8,000 rows, right? You get given a batch of rows and you have to produce a batch of output rows. And then you can, depending on what your function is doing, you can take it, like use all the different, there's a whole bunch of kernels in the Arrow library that do things like calculation of them really fast, or like there's a whole bunch of ways to make those functions quick. But
okay, I'm a little bit surprised I get it on the row or batch of rows level rather than the individual column value level.
well, I mean, you get the column values for a bunch of rows at once.
So do I have to include some logic to deal with the fact that I'm doing more than one function call? Like if I was re-implementing uppercase,
Yes.
I just get a string in and a string out, or I get a batch of rows.
You'd get an arrow array in is what you'd actually get, a string array in, and you have to produce an arrow array out.
Okay, so there is a little bit of the machinery I have to worry about around the transformation I'm interested in. Gotcha.
Yes. However, I think there's enough examples of how to do that. Like you can write that in 3 lines, basically.
Okay.
Or you can write it in like 100 lines. The 100-line one's going to be a lot faster because you're going to take care of a bunch of special cases. But the 3-line one's going to work fine for you. And so I think that in my mind is also very nice, where you can kind of start with it's actually how we implement a lot of these functions initially. Like you just kind of implement the simple version, and then as people care about it, they'll go do things like optimize away string allocations or whatever, which is, makes them more complicated, but they go faster. And so over time they get better.
Right. Yeah, I can see that. So I want to pull out one more layer then to what are the most interesting projects using DataFusion, do you think? I'll give you one more plug of InfluxDB for time series.
Yeah. Clearly InfluxDB is using it for a time series in both, all the different 3.0 product lines. There's quite a few other database companies there's a whole bunch of people who are doing various observability, like other time series databases or logs or whatever. It's still shocking to me how there's still new companies all the time coming up with products for that. So that's clearly not a solved problem for me, but a bunch of people are building observability products on top of DataFusion.
Right.
There's a bunch of people building, and then there's a bunch of like various other specialized databases. There's a sequence of people who are basically trying to take over some or all the workload of Spark. Right. There's a whole Spark is huge and it's very well.
Yeah.
And so we see there's like a subproject of DataFusion called Apache Arrow Comet, which is trying. I don't know if you're familiar with something called Velox, but
no.
And so you have to. All right, I'll give you that. So Spark is an entirely Java-based engine, right? Just when you start with it, it's very, very popular in the data processing world. However, as soon as you start running it on large data volumes, people immediately realize, well, hey, it's spending a huge amount of time in the JVM that we could make better. And so one of the first things Databricks did, which is a big Spark vendor, right, is they implemented their own custom execution engine in C++, right? That has the same semantics of the Java one, but it's and so you still sort of interact with it as a Java front end, but then when it actually goes and runs the code, it runs in C++. And there's been a bunch of other people trying to, but that's proprietary. It's not open source. So Facebook made a non-proprietary, still proprietary, but it's open source called Velox, right, to do basically the same thing to try to accelerate the workloads. And then a bunch of guys at Apple and others are trying to build something similar on top in Rust using the DataFusion lower level primitives, right? Like if you want the fast parquet reader, you just use DataFusion's fast parquet reader and stick it into the Spark plan. That's obviously skipping a whole bunch of the details. But it also seems that a bunch of people have been using DataFusion to try to move some of the Spark work, do whatever they've been doing in Spark, do it more efficiently due to DataFusion's native Rust implementation, right? So there's this Comet project to try to replace the whole execution runtime, but there's also been people who are trying to offer sort of Spark compatible engines to do whatever people want to do, but faster and more efficiently. So like SailHQ is an example of someone doing that. I think there's other more interesting. So there's a whole bunch of database people doing lots of database stuff. There's the streaming systems like I talked about, like Arroyo or Sonata, and there's some other ones too. And again, these are the ones I know of. Like and no one has to tell us that they're using DataFusion. So like I don't know all of them. Right? They just know the ones who bother to tell us.
Yeah.
Also, interestingly, is that the table format. So like Apache Iceberg and Apache or Delta RS or Delta Lake rather, and Hootie. Those are table formats. So those are like adding a little layer of metadata on top of a bunch of files that live on object store, so you can kind of treat them as tables. Interestingly, so the first versions of those are typically written in Java because it kind of from like the Hadoop-ish kind of world. But all the Rust implementations, if you look at them, they all use DataFusion under the covers because those table formats require you to basically do some amount of processing on the data. Like compaction is basically you got to resort the data, right? Like DataFusion has a lot of low-level operations to resort data really fast, right? Write Parquet, like we can do that, right? Or read Parquet really fast. So there's a whole bunch of so that's kind of cool. An interesting use case. And then also you see new other people trying to provide different data formats. Like there's a company, LanceDB is one, sort of has an AI machine learning focused file format and database system.
Of course, there are going to be a lot of people doing it for AI right now.
Yeah. And then
data pipelines.
There's a company called Spiral, I think is the company, but Vortex is the name of the product, which again I think has a specialized format for certain workloads that they use DataFusion. I think they also connect to DuckDB too. But so that's kind of those are some other interesting use cases. Another fascinating one that I found was people actually like a company called SDF, which was recently acquired by DBT. I know that's a lot of like 3-letter acronyms, but DBT is like this data preparation tool that I think is quite popular. SDF had a similar type of tool, but what they use DataFusion for is for helping companies that had like big collections of SQL queries that basically did ETL, right? Like so you basically describe data processing as terms of a bunch of ETL stands. That sounds very fancy, but it's basically like you run a bunch of queries to generate reports, right? But like typically it's not just a single query to generate a report. It's like it goes through 5 different levels or 10 different levels, who knows what. And so by the time the data comes out the other end, it was very hard to understand like, well, is there any personally identifiable information that came there, right? Or is this was this derived from a certain source or not, right? Because it all got mushed together.
Yeah.
So they were doing some sort of data provenance analysis, right? Where they'd basically take a bunch of SQL queries and then figure out how the data flowed between them. But the way they did it was I think they had their own parsers, but then they built the DataFusion logical plans, and then they did this sort of data flow analysis thing over the DataFusion logical plans.
Oh, that makes a lot of sense. Yeah.
Which was kind of interesting because that's a use case like where it just used the front end of DataFusion, like it didn't use the execution engine, at least initially, or the SQL planner for that matter. It was just using the logical plan stuff. And I think over time, what happened is now that they had the whole engine in there and they had a logical plan, they could actually, not just could they understand what the SQLs did, they could actually run some of them or all of them, right? And so you could do like, not just could you understand what the thing is, you could maybe like test it out locally or whatever. So
yeah, that's a really nice way to sneak in with an analysis tool and end up with a database.
Yeah, and so there's some of the.
That's cool. That's cool.
And there's some other people who tried to put like they tried to basically do it. There's a company called Seafowl, I think. I'm not exactly sure what's going on with them at the moment, but they got acquired by Enterprise DB, which is the guys like an enterprise version of Postgres, for trying to build like basically a special analytics engine in Postgres. Like Postgres is a traditional row execution engine, but they are trying to add various features to make it faster for analytics. So like doing large aggregations over large numbers of rows or whatever.
Yeah, that makes sense.
And the Seafowl guys had like a Postgres extension that would basically use the DataFusion engine to calculate some of that stuff.
Oh, okay, because Postgres is C, right? So they're mixing in Rust into that. That's perfectly feasible.
Yeah, I don't honestly know exactly how the machinery worked, but that was the high level.
Yeah, that makes perfect sense.
Yeah.
So what about you? What's your next thing to work on in DataFusion?
Well, I've got this TBCH data generator that I'm currently obsessing about, and the explain plans is cool. I also want to make, I have a whole bunch of things. I personally want to make it's super weenie, like the actual evaluation of predicates when you're scanning Parquet files, right? Like this is like the lowest level when you're running a query against a large amount of data and like you're filtering and you're only picking certain rows, right? Like I'm very proud of how much technology is in the DataFusion and Parquet reader stack right now. Like it's basically as good as I know of in any open source implementation, and quite a bit better than ones that are probably not open source. But it has one thing it's not yet on, which is like called filter pushdown, and it's I don't know how much you care, but like, if you're reading a bunch of rows and like you apply a filter to just one of them, or reading a bunch of columns rather, you apply a filter to just a few of them. Right now, DataFusion will like decode all of them and then throw most of it away. And so there's a much fancier way, like you evaluate the predicates just on the rows you care about, or you evaluate the predicates on the columns that are required, and then only decode the columns that pass the subsequent predicate or pass the first ones, so you don't.
So this is like, I'm just trying to form a mental model. If I were reading lots of large JSON objects, I could just dive into the specific column and see if it's worth decoding the rest of the JSON string.
That's an excellent example.
Yeah.
Yes.
Oh, that's very clever. Yeah.
So we've had that, like that feature has been in for a long time, but it's not on by default because for certain cases it slows things down for really low level technical reasons that my intern, you can read about. It's a very awesome blog post he wrote about it. But he basically has a way to fix it now, and so we just need to like we understand how to do it now. It's just we just got to push it over the line. So I would very much like to do that because it'll get us that much more sort of performance, especially on some important benchmarks.
Yeah, I can see that.
So in my mind, that's a major performance boost. We go improve explain plans, and I also want to make it easier and easier for people to use DataFusion to build engines that operate on data that lives on remote object stores. Right? You can already do that. DataFusion's great; it works. But if you really want to get like maximum performance out of, like, if you want to build a system that really does really well about reading stuff off a remote object store, you still have to apply quite a lot of engineering yourself to make it work really fast. And so I want to lower that barrier as well. So part of that's like making it easier to use multiple runtimes, right? Like we were talking about earlier. Part of it is making it easier to understand and take advantage of, like, how do you get the maximum read throughput from a remote object store, right? Like if you're reading off S3 and you have a 100 megabyte file, say, if you make a single request, that's actually often much slower than if you made like 10 individual requests, each for 10 megabytes in parallel. And there's a bunch of other ways to optimize that. Now, you got to be careful though, because not everyone wants, because it's a genius business model, by the way, right? So Amazon, like, you can read this 100 megabytes with one request and you pay for that one request, but it's kind of slow. So if you want like faster bandwidth, well, what you can do is, in fact, they suggest is you actually, do this chunking idea where you make multiple requests. However, right, you also now pay for each one of those requests. So you actually, there's a trade-off there. But the bandwidth is now much higher because each individual connection is kind of throttled on what its bandwidth can do. But if you're running them in parallel, and then there's a similar thing you can do if you really care about latency. You can do this thing called racing reads, where like object. I don't know how, this may be again too much in the weeds, but if you make a request to object store to S3, sometimes you'll get the data back in like 100 milliseconds. And sometimes it'll inexplicably be 300 milliseconds for reasons you have no idea why. But sometimes it'll be 50 to when you get the first byte. And there's some distribution that's probably due to how it's like you don't have any visibility into why, but it's probably due to which particular machine S3 server you got it routed to, and whether it was cached or blah blah blah. Like, who knows? But the point is a distribution of latencies. So if you want to guarantee that your requests have low latency, and for some workloads latency is really, really important, one technique is you start a bunch of, like, you basically make the request 3 different times for the same part of the same file, and you pick the one that comes back the first. Go back first.
Right? If you really care about latency, you're paying 3 times as much, but it's a lot faster.
Yeah, and well, it's basically, it's typically got much lower P99 latency, so you don't have these like long tails of like sometimes randomly your request is really slow for some reason, because when that does happen, you would have made a second request that got to some other server that was less overloaded or whatever and got back faster to you. But now you're paying Amazon that much more money. So there's a bunch of stuff.
Does this mean in the future we'll look at an explain plan and it will also include dollar costs?
I think it should. Like, that's an example. Well, DataFusion probably won't do that, but that's exactly the kind of thing a system built on top of DataFusion could do. Right, it'll let you tweak the knobs. In fact, there's a whole bunch of interesting, like, I think Dask, is it Dask? Not Dask. Daft. A couple of these new tools are basically like, trading in the fact that it's super easy and good to integrate with these remote object stores. but I feel like they're going to end up having to reinvent their whole execution engine, which is a lot of work, right? So like,
yeah,
it's a lot of people. Like I think there's a lot of opportunity if you make it easier that people can basically go build really cool tools without having to reinvent stuff.
Yeah, well, I'm not going to talk about it, but I've got a secret side project that this might actually solve a lot of problems for me. Right. So I'm going to get on with that. I'm going to send you back down the Rust mines to work on DataFusion. Yeah, Andrew, thanks very much. That was fascinating.
Well, thank you so much for letting me blather for so long. All right.
Cheers. Thank you, Andrew. So here's a fun thing I found out after we recorded that interview. I've been working on a database-like thing. It's not a database, but it's in that space. And I don't know if it's a research project or a hobby project or if it's got legs. We'll see. But I've been writing it for a couple of months, and early on I realized I was going to need an SQL parser. Started writing one, realized it was going to be a real-time sync, so I just went to crates.io and searched SQL parser, picked the first decent-looking option, and I thought, I'll wire that in for now, and if I need to, I'll rewrite it later. Anyway, it turns out that I don't need to rewrite it. It's actually very high quality, and it's the SQL parser from the DataFusion project. So I've managed to record that whole interview not knowing I've been a user for several months. I guess that's my endorsement of DataFusion. It's so easy to use, you won't even know you're doing it. I'm going to keep using that, and I may even steal some other pieces from that project. And if you want to be in a similar boat, or if you're just curious to see some more details, you'll find links to DataFusion and all the other many projects we discussed in this episode in the show notes. Before you head to the show notes, if you've enjoyed this episode, please take a moment to like it, rate it, share it with a friend, share it with a social network. If your company has said, you know what, we should write our own database, how hard can it be? Share this episode with them too. Make sure you're subscribed because we'll be back soon. And if you want to support us being back soon for a very long time, check out our Patreon if you want to support the channel. But for now, I've been your host, Chris Jenkins. This has been Developer Voices with Andrew Lamb. Thanks for listening.